Transistors are the fundamental building blocks of computation. You may have heard of TTL logic, transistor to transistor logic. That's pretty much the standard we're using. If we don't get fancy like making some sort of incredible Intel or AMD CPU, high-end CPU, just normal stuff, it's just transistors. You can use resistors and diodes in creative ways to make gates as well, but they don't propagate power as well. They require more power. There's other trickeries. It's just easier with transistors. So unless you have a specific reason, it's just better to stick with transistors. Now, we have gone over this, but now I'm going over it in depth. Not just the general concept of you can do this, but actually compositing transistors, logic gates into actual computation. So I'm going to start with a three-part series. First, we'll discuss putting NPN and PNP BJT transistors in series. Then the second one will be in parallel, and the third will be a mix and match. And you'll just see how incredibly flexible they are, but how incredibly easy. So let's start with the serial arrangement. Like most things to do with transistors, the NPN and PNP, or more generally, N-type and P-type transistors, tend to mirror each other and go opposite of each other. So let's start with NPN. Let's say we have some sort of power input. We have a resistor and a junction. This junction is going to be where our output comes out. Then we have a few transistors, however many we want, and we have our negative. So we could say that these are the inputs, and that's the output. All of this transistor stuff, like, we're going to do serial, parallel, mix and match, all this stuff. You might think it's going to get complicated. It's not. It's incredibly simple. Here's how you look at it. Is this conducting? Yes or no? It's all binary, right? It's all binary, because you think of logic gates, you think of exclusive or, and all these other ones, and some of them have more complex math functions. Yeah, but we're going a gate at a time. A gate is your power, a resistor, transistors, and the other end. That's a gate. Whether they're serial, parallel, whatever, you're going to have a connection to positive, a connection to negative, one resistor, and a bunch of transistors. That chunk is a gate. And the output of that gate is either is it conducting or is it not conducting, as in through the collector to emitter junctions. If these are not conducting, it's like this is an open circuit, right? They're not even there, right? Nothing's going through. These, since they're NPNs, these would all be 0. So you've got your positive, a resistor, and whatever. So essentially, this output is high. It is just the positive power. And you say, well, the resistor is going to have a voltage drop. Yeah, it will. But that depends on whatever's after this. It doesn't matter for the gate output. The gate output is, let's say this is 5 volts, it's 5. It's high. It's true. And then whatever circuitry after this will use that voltage, and Ohm's law might reduce this, or it might be a MOSFET, and then this will basically not be conducting, whatever. All that matters is whatever's plugged into here has direct access to high when this is not conducting. So the output is high when it's not conducting. When it is conducting, you have a short to ground. The collector to emitter junction, when in saturation, remember, we're not using the beta at all here. We don't care. It's off or on. This is binary. It's easy. Forget all the amplification stuff. The transistor will be in complete cutoff mode or complete saturation mode. Completely closed, completely open. So the collector to emitter junction will have a negligible voltage drop. It will have one, but maybe 0.02 volts, maybe 20 millivolts or something, we basically ignore it. So unless you have 300 transistors in a row, it's not going to do anything. You treat it as 0. So when these are conducting, you have a short to ground because you're Kirchhoff's loop, right? So here's positive through one resistor, through basically wires, out the negative, which connects to the positive. So that's a loop. Doesn't matter here, doesn't matter here. This is one loop, therefore, you can calculate it. So there's basically one power source and one resistor. So you have, let's say 5 volts, so this is going to have a 5 volt drop. So you're pretty much directly connected to 0 there. So when these are not conducting, they're not there, and you just have the positive with a resistor going to whatever. When they are conducting, you have a Kirchhoff's loop through it, so all the voltage is here, and you got 0 going out. And it is a short circuit, so you're going to have to think about that. If you are doing work inside your chip, then you're going to have to pay attention to that. Now, if you are just using NPNs and chaining them, you don't have to worry about it because what you're short-circuiting to is 0, and 0 0 does not activate an NPN transistor. So if you have layers and layers and layers of NPNs, you don't have to do anything because it'll short to 0, but that turns it off. So there won't be any flow. A short doesn't matter if there's no flow. If you connect this to a PNP transistor, then you're going to want a resistor because the PNP is going to get turned on by the low, and then it's going to start shunting power short circuit out this. But I'll get further into those details when I get into combining and manipulating. Right now, we're just working on one gate. So, like I said, keep it simple. Is it conducting? Then you're going to get a short to something. Is it not conducting? Then you're going to get this, pull up or pull down, essentially. And that's it. Now, what operation is this? Well, in order for this to conduct at all, every single one of these has to be 1. Because if any of these is closed, then it'll try to conduct, but it won't be able to. It won't be able to get all the way from positive to negative. So all 1s, and when it is all 1s, when it is conducting, it's 0. So 1, 1, 1 equals 0. Now we know that the AND function is all 1s equals 1. So this is NAND. It's the opposite. All 1s equals 0. Again, you've got complex operations like exclusive OR, but on an individual gate basis, it's all or nothing. You're going to have one value when it's conducting and the other value the rest of the time. So all 1s conducts to 0. All 1s equals 1 is AND, so all 1s equals 0 is NAND. So NPN in serial is a NAND gate, not AND. Now, what if we were to flip it? And I have gone over this again, but let me re-emphasize it in this context. What if we do this? All I did was put the resistor at the bottom instead of the top. When it is not conducting, these are not here, and you've got to pull down to 0. So when this is not conducting, you have a 0 output. When all of these are conducting, you have a short to positive. So again, remember your resistors if you need them. But like I said, you've got a loop from positive through essentially wires through a resistor, negative out to positive. So power supply, resistor. This is taking the full voltage drop. So this is essentially at the positive. Now, what's the problem here? If you were using MOSFETs, you'd be done. This would work perfectly fine. And it would be an AND gate because all 1s conducting equals 1. See, when they're all conducting, it's open to a short to positive. That's high, that's 1. If we're doing 0 or 1, binary. If any of them are not conducting, if any of them are 0, then it shorts, or not shorts, but it is through the resistor to 0. All 1s equals 1, 0 otherwise is AND. Put the resistor up here, it's NAND. Put the resistor down here, it's AND. You can negate any gate, parallel and serial, by flipping the resistor. Because again, remember, there's a voltage when it's conducting and a voltage when it's not conducting. It's one or the other. Just keep it simple. It's one or the other. There's one voltage when it's all closed, one voltage when it's not. If you flip the resistor, you're switching which voltage is which. So you're flipping the sense. That's it. Now, what's the problem with BJTs? If we have a 1 here, if we have on, if we have high, base to emitter is going to be forward biased, which means it's going to conduct. But if these two are 0, and let's be clear, 0, 0, 1, and power is 1, and down here 0. So you would think that the output would be 0 because it can't get to the positive power, but it can get to the positive power here. 1 to 0. Forward bias, the base to emitter junction. It's not conducting through the transistor, but it is conducting through this resistor. If you've got 1 going through to 0, you have conduction through the base to emitter junction, which means you have conduction through this resistor. If you have current through a resistor, by Ohm's law, you have voltage through a resistor. So by whatever value it ends up being, you're going to have a higher voltage than 0 here. This is going to bring it up, and your output is going to be above 0. Is it going to be too high? Well, experiment. Hook it up, and maybe it's not going to be too high to work with. If you're inputting into something that says, okay, 0 to 1.5 volts is still a 0. But if you're chaining to another NPN, this base to emitter here is going to be enough to activate the next base to emitter. So you're not going to get a high, but you're going to get enough to turn on transistors. So that's the difficulty. So an NPN in series NAND gate cannot be an AND gate just by flipping. You can with MOSFETs, you cannot with BJTs. Now you can test it, and I'll show you the voltage. You can test it, and if the voltage is not too high for the next stage, you can do it. You just got to make sure what the voltage is and make sure it'll stay there. Now what about PNPs? PNPs are just essentially the opposite when we're talking about binary logic. The base is high, the PNP is not conducting, the base is low, 0, the base is conducting, and it goes emitter to base and then emitter to collector. So it's the same thing as before. Are they all conducting? Yes or no? You get a voltage either way. For this arrangement, they are conducting if all of them are 0. If every single one of them is 0, then you get a 1 because You have a resistor, essentially wires through the power. So this is taking the full voltage drop, so we're up at the high voltage. If any of them are not conducting, they're not there, you've got 0 connected through and going out. So if all of these values are 0, you get a 1. Well, the OR function says if all of the values are 0, we get a 0. If any of the values, all of them, one of them, any of them, are 1, we get a 1. That's OR. You get a 0 only if and only if, all are 0. In this case, if all are 0, you get a 1, so it's the NOR function. NAND and NOR. For NPNs, it's NAND. For PNPs, it's NOR. And both of these are what are considered the universal gates. NAND and NOR, individually, can be used to composite into every single logical function possible on the planet Earth. No matter how many inputs, no matter how complex. You might run out of space on your board, but you can do it. So isn't that a nice symmetry that they each are the universal gate? And again, it's flipped. This is the normal arrangement, because the emitter to base is what can leak. And in this case, all the bases go out there and never through this resistor. So this resistor is nice and clean, but if we flip it, if we put the PNPs in the arrangement the NPNs were in, then we have the same problem with leaking. Let's say both of these are 1, which means not conducting, but this is 0, that's conducting, 0 and 1. So even though the entire thing is not conducting, and this output should be a completely unadjusted connection to output, right? This should not be here. You should just have high voltage here, and then the resistor is just whatever connected to here, and then what the resistor does depends on what the rest of the circuit is. It could be a MOSFET, whatever, but essentially we treat it as if this is straight to high voltage, but it's not, because the emitter to base junction is forward biased, 1 to 0. So you have no connection, no conduction through emitter to collector, but you do through emitter to base, so there is a current going this away. There's a voltage drop because of this current. Now, pretend that nothing else is in the circuit. Pretend you just have this resistor, this power, and just wires. Ohm's law, you have voltage equals current times resistance, so current equals voltage divided by resistance. So this voltage divided by this resistance gives you the maximum current through this entire thing. Ideally, with this completely closed off, every single bit of that current is available to go to the output. But instead, we have emitter to base is taking some of the current, which is taking current from here, which is affecting how much current can go out there, because it's splitting. All right, there's Kirchhoff's other law, the more obvious but no less important one. Current in equals current out. So that's going to affect the voltage that this has. It's a little more complex to look at, and it's not really important either. The point is, it's affecting it. So you have to test and see if it's affecting it too much. I'm not going to go into a circuit analysis of this. It's not relevant. Just plug it in and see if the voltage you get is workable. See if the current you get is workable. See if anything you get is workable. So if this were workable, if this were MOSFETs, we flipped it. We had NOR before. Now we have OR. If all of these are 0, if all of these are 0, they're all conducting, and we have a short to 0. If they're not conducting, pretending when there's no leakage, then we have a connection to positive. So all 0 equals 0, otherwise 1. That's OR. NOR became OR. So you flip the resistor, you just negate the whole thing. So these are the simple principles. One gate is just conducting or not conducting. You've got 2 voltages. Flip the resistor, and you negate the logical operation. NPN in series is NAND. PNP in series is NOR. And if you don't worry about the leakage, you can flip the NPN in series backwards to be AND, the PNP in series to be OR. So let me quickly show you with the breadboard. I'm using simple NPN and PNP transistors, the 2N3904 NPN transistor and the 2N3906 PNP transistor. These are ubiquitous. You'll find these in starter kits everywhere. They're just bog standard, you might say. I have a 5-volt power supply, which I'll just give a current limit so it reads 5, and I'll be reading the output with my multimeter. There's a reason I'm not using these LEDs to demonstrate it. I'm using the voltmeter instead. I'll get to that in a future video. It was related to a problem I had. And this is a simple input board. It's just power connected through 5 SPDT switches, so they're always connected to 5 or 0. There's no open circuit other than when they're switching and bouncing. And it's got resistors and LEDs in parallel just to show the output, but that has no effect on the circuit. And I'm using resistors that are 10,000 ohms, 10k ohms. So let me connect from power. Let's do the NPNs first. So first I need a resistor. The resistor goes at the top near the power for NPNs. So I'll connect to the first collector, out the emitter, and just on down the line through 5 NPN transistors. I'm just connecting the emitter of one to the collector of the other, and the final of the 5, I'll connect its emitter to negative. So then over here, so I've got a 10k resistor for that gate. Each of the inputs, I have a 10k resistor on as well. So I'll connect input 1 to the base of the first transistor, and so forth. Just one input per base. So now the gate is active. I will connect my meter to the output spot, which is between the resistor and the first transistor. So right now we're reading roughly 5 volts. Remember, it's NAND. All of these have to be 1 in order to get a 0. So if I turn on one of them, turn on another, just turn on all of these except one, turn this one off, turn this one on, we're just keeping roughly to that 5 volts. And then if I turn them all on, when I turn the last one on, we go down to about 0. 0.07, 0.08, remember how I said there is a voltage drop across the base, across the collector and emitter? With 5 transistors, it's definitely visible, but 0.07 for 5 transistors, you can basically ignore it. So there's your NAND gate. Every single one of them has to be on in order to get a 0. If any of them are off, you get a 1. In this case, around 5 volts, a high level. Very simple. Let me turn everything off, and now I'm going to flip the resistor to the other end and try to make an AND gate. So let me remove the connection to the first collector and the last emitter and the resistor. So I will connect directly from power to the collector of the first transistor, the output, the emitter of the last transistor, through the resistor out to negative, and then I will measure, to negative I said, I will measure the current, or the voltage rather, between the last transistor and the resistor. So now it's before the resistor instead of after it. With all of them off, we're getting a 0. If I turn on the first one, second one, third one, even the fourth one, nothing at all, right? No voltage change, we shouldn't. I should have to turn on all 5 to get high, and if I turn on the fifth one, we get, 4.12 volts. So the leakage, even if all of them are on and conducting, you're still getting that one leakage. So let me turn them all off again. And let me turn on just the last one. 2.14 volts. So it's more than just the base to emitter forward voltage drop. It's based on the current. If you turn the current down, it might. For example, if I turned up this resistor, it might actually go down. If I turn on just the fourth one, nothing. So we're getting 2 and some volts with the last one on. This is just through the base to emitter. The current going through this signal into the base and out the emitter, through the resistor and out, is enough to cause this much of a voltage change. And then if I turn on the second one, the third one, the fourth one, and the fifth one, that was in reverse. That was 5, 4, 3, 2, 1 actually, but you could see that. The voltage goes up. If I turn off any of them, it's having funky effects, as you can see. Any of them that are connected will combine their voltages, but any that are not will not really affect it. So it's unreliable, but it is stable. These numbers I'm getting as I flip these on and off, the numbers are staying the same. So you can look at these voltages and see if it's all right for your circuit and do it. But keep in mind, temperature changes. If you change the circuit later, you have to reanalyze everything. I would recommend not doing it. It's just not worth it, but it's an option. I wanted to be clear that it is deterministic unless you change the circuit. So now let's do PNPs. So remember, the resistor goes on the bottom for PNPs naturally. So I'll go straight from power into the first emitter and connect each collector to emitter as I go down the line of PNPs. And then the final emitter will get connected through a resistor and out to negative. So then I'll connect the inputs, the same as before, 1 to 1 to each base. And now finally, I'll measure between the last transistor and the resistor. And with all of them 0, we're getting roughly our 5 volts. So remember, a normal OR function, all of them 0 to get 0. So NOR, all of them 0 to get 1. If any of them become not 1, or not 0 rather, if any of them become 1, then it turns to low. If I turn any single input high, then the voltage goes low. There's your NOR gate. Let's turn them all on. And of course, we will just stay right at 0. So there you go. There is your regular NOR gate. Now let me flip the resistor again. Disconnect the last emitter, or the first emitter, the last collector, because they're PNPs. Disconnect the resistor, and now I will connect from positive through a resistor, out the resistor to the first emitter. Isn't it annoying how it's called collector and emitter? Anyway, anyway, out the last collector, the negative, and then I will connect my meter between the first resistor, between the resistor and the first transistor. So now we should have an OR function. All of them 0 to get 0. If I turn any of these on, we should get 1. But all of them are off. None of them are conducting, or rather all of them are conducting, because all of the emitters are high, all of the bases are low. But we're not getting our 0, we're getting 0.83. It's too high. If I turn off, let's say, the first one, then we go all the way to 5. That's great. And if I turn on any of the others, there's basically nothing going on. With that first one, the one next to the resistor on, I can do anything I want with these and it's going to have very little effect. But if I turn off the first one, turn on the second one, turn on the third one, turn off the second one, turn on the fourth one, the fifth one, see, we're getting these weird values again. It's leaking again. And if I turn them on in reverse order, you can see the voltage go up and up and up until finally the last one turns on and we get near our 5. So again, if you don't change the circuit, you get reliable values based on different configurations, but this is fragile. This is not something you should rely on. Even if it is technically reliable, you shouldn't, because you're going to change something else and forget, and it's all going to go haywire. Whereas in the other direction, it's all going to be within tolerances. So you can, but you shouldn't. Now you know. Digital logic with transistors is great. It's easy. It's ones and zeros, ons and off, highs and lows, positives, negatives. You don't have to worry about betas and beta independence. You don't have to worry about any of that. You have 2 voltages per gate. One is if it's conducting and one if it's not. And if you flip the resistor, if you can, then you just negate the logic operation. NOR becomes OR, NAND becomes AND. And from these NAND and NOR gates, you can build every other gate, but there's a little more flexibility built in. There's no reason to use more transistors than you need to, after all, especially if you're paying for it and if you're trying to sell it. So we'll discuss parallel arrangement and we'll discuss mixing and matching, but until we do, I'll be seeing you.